Hello guys, welcome back to my YouTube channel. In this video, we'll discuss about changes to moment arm of a force, which is a subtopic of torque revisited. Now, first we'll define what is moment arm. Okay. Now, this is the thigh and the leg foot segment, that is a knee joint which is flexed to 90 degrees. Okay. Now, this is the point of application of the quadriceps muscle force vector, which acts in this direction, and it is designated as QLF. Okay, and a gravity weight foot leg foot segment. Okay, this is a gravity weight foot leg foot segment. Now, the gravity is another force and the weight put on the leg foot segment is another force. When we compose these two forces, we got a resultant force known as gravity weight put and leg foot segment. Okay. Now, in order to define the moment arm, we need a force vector. Okay. Now, we got the force vector. I'll define the moment arm with respect to the quadriceps muscle force vector. Now, this is the joint axis of the knee joint, which is located on the lateral condyle of the femur. Now, the moment arm is defined as the line that is perpendicular to the force vector, and joins or intersects the joint axis. Okay, I repeat guys, moment arm is defined as a line that is perpendicular to the force vector and intersects the joint axis. This is known as moment arm. Okay, now we will locate the moment arm of the gravity weight foot leg foot segment force. Now, if we extend this line, okay, this force vector intersects the joint axis. Okay, whenever a force vector, in order to draw the line, okay, when it intersects the joint axis, its moment arm is said to be 0. Okay, hence the moment arm of the gravity weight foot leg foot segment force is 0. Okay, now by extending this force vector, the effect of the force and the magnitude of the force does not change. Okay, they remain same. Even though if we extend the line, the effect and the magnitude remains same. Now, as we know, the torque formula, torque is equal to force into moment arm. Okay. Now, the force exerted by the gravity weight foot leg foot segment vector is minus 88 newtons. Why I designated minus 88? Guys, please do watch my torque video in order to know about all these negative and positive signs. Okay, in detail I explained in that video. Now, the force is minus 88 newtons. Okay, and the moment arm is 0. Hence, the torque is equal to 0. The torque is 0 with respect to gravity weight foot leg foot segment force. Hence, this force has a negligible amount of effect on this leg foot segment. Okay, and it does not produce any rotatory motion of that segment, of this segment. Now, when we comes to quadriceps on leg foot segment force, it's, for example, its moment arm is 0.03 meters. Okay, now the quadriceps muscle force requires a very small force. Okay, this force vector requires a very small force with respect to that of a larger momentum of its. Hence, the quadriceps muscle force will produce as a net extension torque of the knee joint in this direction. Hence, the knee extension is a counterclockwise in a counterclockwise direction, and it is designated as a positive sign. Okay guys, okay, this is about the changes to momentum of a force when the segment, that is the knee joint, is at 90 degrees of flexion. But this will not be same as the leg foot segment changes. As the leg foot segment changes, the force remains same maybe, but the moment arm and the net torque production keeps on changing. Okay, now we'll see this example. In this example, the knee joint is flexed nearly to 45 degrees of flexion, that is, it is going into extension. Now we again locate the moment arm of these two forces. For example, this is the force vector of the gravity weight boot leg foot segment, and the quadriceps muscle force vector is acting in this direction. Okay, now if we extend this line, this is the joint axis. This is located on the lateral condyle of the femur. By extending this line and draw another line which is perpendicular to this force and intersecting the joint axis, and this line is the moment arm of the gravity weight foot leg foot segment force vector. Okay, now for example, if this moment arm is 0.27 meters, that is, it has increased from 0 to 0.27 meters. Okay, now this gravity quadriceps leg foot quadriceps muscle force vector, we will locate the moment arm. Okay, this is the moment arm. The line is perpendicular to this is the quadriceps force vector, muscle force vector, and intersecting the joint axis, and this is the momentum. Now for example, the quadriceps muscle force vector momentum has increased from 0.03 to 0.05 meters. Now it has increased from 0.03 to 0.05. Now as I said, this force, the gravity weight boot leg foot segment force, is exerting a force of 88 newtons. So if we calculate the torque of this force vector, we will get force is 88 newtons and the new momentum, which is increased from 0 to 0.27, okay, we will get a net torque of 23.72 Newton meter. Okay, this is the net torque exerted by the gravity weight boot leg foot force vector. Okay, now if this is not, this net torque produced by this force vector is not balanced by the quadriceps muscle force, then the leg foot segment will move into a flexion movement. Hence a net flexion torque is produced, but the quadriceps muscle force will also exert a force that equally matches this net torque produced by the gravity leg foot segment force. So, in order to maintain the segment in a rotatory equilibrium. So, how much force has to be exerted by the quadriceps muscle force? We will see that, guys. Now, if we calculate the torque here, torque is equal to force, quadriceps muscle force has to exert a 475.2 newtons into the moment arm is 0.05 meters. So, in order to maintain the segment in an equilibrium, rotatory equilibrium, the quadriceps has to exert a muscle force of 475.2 newtons. If we calculate these two, we will get a net torque of 23.72 Newton meter. Okay. Here this force is exerting a force of 88 newtons on the leg foot segment, and its new momentum when the segment moved into nearly 45 degrees of flexion or it is moving into an extension, the net torque produced is 23.72 Newton meter. If the quadriceps muscle force is not not maintaining this, not maintaining the equal force, then the segment, the leg foot segment will move into flexion. So, how much force does the quadriceps has to exert? That is the question. The answer is 475.2 newtons. In order to get, when we calculate with that of 0.05 meters of momentum, so we will get 23.72. Now 23.72 and 23.72 of these forces, two forces, and then the segment is said to be in rotatory equilibrium. Okay, now the segment will maintain in this position, in this nearly 45 degrees of flexion, knee flexion movement, but in order to move the leg foot segment into an extension torque, extension movement, the quadriceps has to exert a greater force, that is greater than 475.2 newtons, in order to move the leg foot segment into extension, that is knee extension. Okay, guys. Okay, this is with respect to when the knee is in 90 degrees of flexion, when the knee is in 45 degrees of flexion, how the moment arms and the torques are changing with, of these two forces when the segment is in different positions. If we take this representation, that is the knee is in full extension, that is 0 knee flexion. Okay, in this also we will represent the force vectors, okay, and the moment arms. Now the first is gravity weight boot leg foot segment, the force vector acting on this. Okay, this is acting in this direction and it exerts a force of 88 newtons, minus 88 newtons. And now the force has not changed when with respect to when we see the other previous examples also. Okay, the force remains same, that is minus 88 newtons. Now the force vector of the quadriceps muscle group is, the point of application is at the tibial tuberosity, and the force vector in this direction, which is designated as QLF, quadriceps muscle force vector. Now we will represent the moment arms. Now this is the joint axis of the knee joint, which is located on the lateral condyle of the femur. The moment arm is the line, perpendicular line joining the force vector and intersecting the joint axis. Okay, this is the moment arm of gravity weight boot leg foot segment force. Okay, now the moment arm for this quadriceps muscle force is This is the one. This is the momentum. Now, the quadriceps muscle force vector has reduced in has a reduced momentum from 0.05 to, in the previous example guys, when the knee is nearly 45 degrees of flexion. Okay, now it is reduced from 0.05 meters to 0.01. Okay, it has further increased, but the momentum of the gravity weight foot leg foot force vector has increased from 0.27 to 0.36 meters. Okay, this has increased further. Okay, now if we calculate the torque of this force vector, that is gravity weight foot leg foot segment force vector, torque is equal to force is 88 newtons and the moment arm is 0.36 meters, will get a net torque of 31.68 Newton meter. Okay, 31.68 Newton meters of the net torque is we will get with respect to gravity weight foot leg foot force vector. Now, if we calculate this torque is equal to torque with respect to quadriceps muscle force vector, we got a momentum of 0.01. Now, in order to balance this leg foot segment in an extended position, that is knee extension position, how much the quadriceps has to exert a force, that is the quadriceps muscle force has to exert a force of 3168 newtons force in order to get the net torque of 31.68 Newton meter torque. Then only the segment remains in an extended position, that is at 0 degrees of knee flexion. Otherwise, if the quadriceps muscle force does not exert 3168 newtons of force, then there will be a flexion torque produced by the gravity weight foot leg foot force vector. Hence, the leg foot segment moves into knee flexion. It cannot be maintained in knee extension position. Okay, hence this is a very difficult position to maintain, even though the force is same, that is minus 88 newtons, but the moment arm has increased from 0.27. This 0.27 we got at when the knee is nearly 45 degrees of flexion. Now, when the knee is in complete extension, we got 0.36. Okay, now the net torque is also increased. Okay, now see guys, I'll define one term which is known as a lever arm. Okay, what is lever arm? When the moment arm lies parallel to the segment, this is the leg foot segment, this is the moment arm of the gravity weight foot leg foot segment force vector. Okay, this is the moment arm. This force vector moment arm is lying parallel to this segment, leg foot segment, and intersecting the joint axis. Hence, whenever this happens, the moment arm is termed as a lever arm. Okay, this is very important. This is not applicable in all cases. In most of the cases, we use a moment arm term, but whenever the moment arm is parallel to the segment and intersecting the joint axis, then it is termed as a lever arm. Okay, when will be the moment arm will be greater? When the force is applied at 90 degrees to that of the segment, then the moment arm is said to be greatest. When the moment arm will be 0, when the force vector, when you extend it, as we have seen in a 90 degrees of knee flexion angle, when the action line of the force vector, when we extend it and when it intersect the joint axis, then there in that case the moment arm is said to be 0. Okay, this is one of the toughest positions to maintain, guys. Whenever prescribing any exercise, first it is very difficult to maintain this position if the quadriceps muscle group are very weak, because then here the gravitational force is acting and the weight boot leg foot segment force is acting in this direction. Okay, and the moment arm will be greatest when the force is applied at 90 degrees to that of the segment. Okay guys, this is all about torque revisited, and that the subtopic is changes to the moment arm of a force. Okay, if you like the video, please subscribe to my channel and please share with your friends. If you have any doubts, please do comment, guys. Thank you. Thanks for watching, guys.